So, welcome everybody to this week's OMAS, and today again we have two speakers, and the first one will be Stephania Hernandez, and she will talk about the white dwarf binary pathway survey number 4. And yeah, I would like to ask you to share your screen.
Yeah. Yeah, is this okay?
Yes.
Okay. Can I get started now?
Yes.
Okay. Hi, everyone. I'm happy to be here and present the latest result of our work with the white dwarf binary pathway survey. The survey is dedicated to the study of Postcommon envelope binaries with intermediate mass secondary stars. Our goal is to characterize these binaries to obtain the constraint to calibrate some of the uncertainties of the binary population models. Here is the big picture of the binary evolution, starting with two main sequence stars. As always, the more massive will evolve first into a giant star, which overflow its Rotational, causing dynamically unstable mass transfer, and the entire binary entered to a common envelope evolution. During this phase, angular momentum and orbital energy are extracted from the orbit and unbind the envelope, revealing a closed binary containing a white dwarf and its main sequence companion. These systems are also known as Postcommon envelope binaries. For this survey, we selected only Postcommon envelope binaries with AFGK type secondary stars. White dwarf binaries with AFGK secondary simultaneously can simultaneously sample a huge range of different evolutionary channels, including the supernova 1A through the single or the double degenerate channel. The evolutionary pathway the evolutionary pathway will mainly depend on the orbital period of the system. We face some problems in this project as well. To the first one, the more important for the moment is to identify the Postcommon envelope binaries. And this is because at optical wavelengths, the main sequence star completely dominates over the white dwarf. We overcome this problem by combining optical observations from surveys like RAVE, LAMOST, and Tycho Gaia astrometrical solution with GALEX ultraviolet data. We identify here, I'm sorry. We identify over 1,600 white dwarf with AFGK binaries candidates. And here we present or we plot the main sequence star temperature versus the UV axis. These orange points represent the targets that have a normal UV emission. And this in blue are the targets that have a UV excess from that it's not normal from the type of a star or for day type. I'm sorry. After identify the 16 all these targets, it is necessary to observe them with the aim to detect variations in the radial velocity to confirm the binarity. And after that, do follow-up observations to those systems that show the variation to obtain the orbital period. In red are highlighted 5 objects we selected to study in detail, mainly because they are so similar. 4 of them have G-type secondaries and 1 of them have K secondary, and all have short orbital periods. We perform high-resolution spectroscopy with 5 different telescopes from North and South Hemisphere to maximize the sky coverage. All 5 targets we selected have orbital periods while constraining between 20 hours to 2.5 days. The 3 targets in red have slightly evolved secondary stars. The radius is, we know this because the radio is bigger compared with the 0H main sequence star radius. And the binary we show here in blue, it's actually a triple system with a non-interactive component. It is 330 astronomical units far away from the inner binary. From the entire survey, we observe HST. Well, we observed the 12 binaries with HST, and 11 of them was confirmed to have a white dwarf. And 1 of them results to be as a hot subdwarf. Between these 11 systems, or white dwarf confirmed, it is one of the previous targets which I have showed before. And it is Tycho 110, and we found a strong carbon-4 and helium-2 emission lines in the UV wavelengths, and they are related to chromospherical activity. We obtained the precise white dwarf mass and found discrepancies with the mass calculated with the binary mass function. In the plot, we see in black the HST spectrum and the UV spectrum on this side. I'm sorry, on this side. In purple is showing the synthetic spectrum from the white dwarf, and in green it's the pure hydrogen. I'm sorry. In purple is the synthetic spectrum from the secondary, and in green the pure hydrogen white dwarf. The light green dots are UVs far and near ultraviolet, and in dark and small green dots are the X-ray photometry taken with Swift. We observed this 2 of these systems with TEST, and both systems have, and we found that both systems have rapidly rotating secondary stars, tidally locked with the orbital period. Both secondaries show plenty of flares and star pods. Nevertheless, the difference between these 2 systems cannot be more sharp. Due to that, Tycho 3858 shows short-living spots that appear to remain mostly fixed, and Tycho 110 shows long-living spots that migrate across a differential rotating surface. We also perform MESA simulation to predict the future evolution of our systems. This is the diagram that showed the dynamical and thermal stability limits for limits of the mass transfer in terms of secondary star and the mass ratio. Where the binary is stable if it is under the corresponding line. In the case of the targets in blue or in green will run into unstable dynamical mass transfer when the secondary field fills its Roche law. The orbital energy of the binaries will not be enough to expel the envelope, and therefore the two stars will merge. The evolved, they will evolve into a giant star, with the core of the giant being a white dwarf, well, the white dwarf we observe today. This giant will evolve into a single white dwarf as the final state. Depending on the mass of the white dwarf, we have the chance in these two systems to they enter or not to thermal time mass transfer. And if they enter the thermal time mass transfer, then the white dwarf have the chance to increase its mass. The yellow one, it's the more probable to enter to thermal time mass transfer, and it will potentially be the second known superself source progenitor that we know. The two systems in pink are progenitors of cataclysmic variables with evolved donor, which does not become fully convective, and the angular momentum laws will continue through magnetic breaking until reach the period minimum. These systems will not detach in the orbital period range of 2 to 3 hours. The difference in the size, mainly in the smaller one, it's because the white dwarf, the mass of the white dwarf is well constrained. Previous to this project, very few Postcommon envelope binaries with AFGK companions were known, and now we increased this number to 13 systems, and found that can be identified two populations of Postcommon envelope binaries with an intermediate mass secondary. One of the populations is with a short orbital periods under 10 days and circular orbits, as the same as Postcommon envelope binaries with dwarfed secondaries, and the other population it's with long orbital periods up to 800 days, and some of them have eccentric orbits. These observations can be compared with models and with population models, and we found that white dwarf with AFGK binary secondaries with short orbital periods seems to have or to use the same energy that use binaries with M-dwarf companions to combine the common envelope. But for those systems that have bigger or longer orbital periods, it seems to require more energy or additional energy source during the common envelope evolution. And one of these energy that can be taken into account or can be added, it's the recombination energy. That as mentioned before, we found that some Postcommon envelope binaries with long orbital periods and some of them show eccentric orbits, and that eccentricity in many cases can be explained by the interaction with the third component. 5 of these systems were observed with sphere to confirm the existence of a third object, but only in 2 cases the third object was confirmed. The systems, and therefore all these systems are contaminants for our sample. The white dwarf with AFGK systems with long orbital periods seems that experiment non-stable conservative mass transfer with the white dwarf progenitors start to expand and fill it Rotational. Then they skip the common envelope phase, and some of them do not circularize their orbits. This mechanism then can produce the eccentric closed white dwarf binaries with long orbital periods. These binaries later can evolve through the double degenerate channel and produce the supernova 1A explosion. To finish, I show here my conclusion. Well, the conclusions that so far we identify 6 new Postcommon envelope binaries with this survey. Despite the similarities between these systems, they have different, very different future evolutions. We identified 2 different populations in the binaries, and some of the short ones evolve or need the same orbital energy to unbind the common envelope. The others need extra energy, and well, and that's all. Thank you.
Yes, thank you very much, Stephania. I cannot see any questions in the chat yet, so let's wait a bit.
Okay.
Or you can also raise your hand if you want to ask. So there's one from Ingrid. She says, thank you, very nice talk. What is the mass of the white dwarf in the triple system? Could it be that the systems are younger and didn't have time to secondaries?
I'm sorry. Well, here are the parameters, and the white dwarf. Well, the white dwarf of the white dwarf in the binaries, it's only confirmed for the one we observed with HST, but we estimate the white dwarf of the other 4 systems, and they are estimated to be, I cannot see, between 0.21 and 67 solar masses. I'm sorry, I forgot the other question.
Could it be that these systems are younger and didn't have time to secondaries?
You mean for eccentric? Well, I think they can be, but as they are, well, I am not really sure about triple systems. Maybe Felipe will know a bit more about this. But as they are already, as they are already unbind from the common envelope, I think they are more or less the same age as we observe the rest of the binaries, of the post-common envelope binaries.
Felipe raised his hand, so maybe you can just start speaking.
Yes, can you hear me?
Yes.
Super, great. So just to complementing the answer from Stephania, we don't know exactly the mass of the white dwarf because, well, we only know that there is a white dwarf, but maybe the white dwarf is the third companion. So we have these 2 options. The white dwarf is part of the inner binary, or the white dwarf is part or is the third companion. So yeah, it's not, we are not really sure about the mass of the white dwarf because we have this uncertainty about where is located the white dwarf.
Okay. Then Another question, is TYC110 detected in the X-rays? You were mentioning Swift data, what the XRT data tell?
Yeah, we observed the system with Swift, and we didn't saw any variation in the light curve, in the X-ray light curve. Actually, we didn't see anything. We conclude the system have well, the secondary star have a very active chromosphere, and it shows the emission lines and the spots and flares in the binary.
Okay.
Yes, I saw the last question. Yes, they are consistent with coronal emission.
Yet in between there was another question by Marcelo, and he asked if you can repeat what are the characteristics of the systems with eccentric orbits, masses, semi-axis.
The one I observed, well, they are all these characteristics. Most of the triple systems have eccentric orbits and long orbital periods, but the one I characterize here seems that the triple component is not interactive at all with the Postcommon envelope binary, and the binary have a circular orbit.
Okay, then I cannot see any further question. And also no more raised hands. So I would say I would like to thank you again for your talk. And then we move on to the next talk.